Assalamualaikum. Hello everyone. My name is Fahry Samsudin and I am a semi-finalist for the IWSC 2025 in the field of physics. Today, I will be exploring a system that looks very simple at first glance, just mass on a screen. But here's the twist. What happens when this mass is not only moving up and down, but also swinging like a pendulum? We'll dive into the physics behind this vertical swing pendulum using Lagrangian mechanics, a powerful method to understand complex systems with elegance. So now, to construct the experimental system, only a few basic components are needed. A light spiral swing, a small cylindrical mesh, a rated stand, a vertical rod, and a boss head frame. Here's how I assemble this system. First, I attach the vertical support rod to the base of the rated stand. Second, using a boss head crane, I securely fasten the light spiral swing to the vertical rod. Then, I suspend the small cylindrical mesh from the free end of the swing. This simple setup allowed the mesh to move into way vertically as it stretches and compresses the swing, and horizontally as it swings like a triangle. You can see the actual setup in this photo. What makes this system especially interesting is the both motion of down and side to side are fully free and allowed to interact. There are no constraints on the motion within the vertical frames. That's why the system is ideal for Lagrangian analysis where we focus on the interplay between multiple degrees of freedom in motion. Okay, here we have the system we've carefully assembled. A simple spring and mass setup. But don't let its simplicity fool you. When we pull the mass slightly at an angle, something fascinating begins to unfold. At first glance, you might think it's just swinging like a regular pendulum. But look, it's also bunching, stretching, and compressing the spring as it moves. What you're seeing is a beautiful combination of two types of motion. The first is radial motion, where the spring stretches in and out. The second is angular motion, where the mass swings side to side. But these two motions are not happening in isolation. They are deeply connected. In fact, they are in constant conversation with each other. As the mass swings, gravity pulls the spring off center, which changes how much it stretches. And when the spring stretches, it changes the length of the pendulum, affecting how fast and how far it swings. So rather than we having like a simple pendulum or a simple spring, the system dances between the two, constantly trading energy back and forth. In the language of physics, this is a system with the 2 degrees of freedom. The motions are coupled, not severed, and the result is a rich, dynamic motion that's both beautiful and complex. Understanding this system isn't just about writing equations, it's about uncovering the hidden harmony in how forces interact. So, how do we describe the motion of this elegant system? Let's break it down step by step using the powerful language of Lagrangian mechanics. So we will go to work. Okay guys, in the system, we know a mass M is attached to a spring with spring constant K and natural length L. The mass is allowed to move in a plane, but by stretching or compressing, the spring is called radial motion and swinging is called angular motion. In here, we describe the system in polar coordinate. So, to solve this problem, we will to transform coordinate from polar to Cartesian coordinate. So, in polar coordinate, in the system, sin theta function of time is equal to x divided r function of time. So we have x equal to r function of time sin theta, theta function of time. Cos theta function of time is equal to y divided r function of time. So y is equal to minus r function of time cos theta function of time. So we know r is equal to x I e vector plus y z vector. So L vector function of time is equal to L function of time sin theta, theta function of time vector E minus R cos theta, theta function of time vector J. The minus sign in Y is assumed to downward in the positive direction for the gravitational potential. So in here, we will to find the velocity component because we need for the kinetic energy. We know the velocity is time derivative from the function of position. So in here, R dot vector is equal to d by dt x function of time e vector plus y tj vector. So we have the value here. So we will have the R dot vector is equal to multiple R dot sin theta plus R cos theta, theta dot e vector plus multiple minus R dot cos theta plus R sin theta, theta dot g vector. So we will have kinetic energy is T, and T is equal to 1/2 ml dot vector square. So we will have 1/2 m r sin theta, r dot sin theta plus r cos theta, theta dot square plus minus r dot cos theta plus r sin theta, theta dot square. In here we have to we can use the a plus b squared, and we have sin square theta plus cos square theta. In the identity and in trigonometry identity, sin square theta plus cos square theta is 1. Okay, so t is equal to 1/2 m r dot square plus r square theta dot square. Okay, for the potential energy, we have the elastic potential energy of the spring. Potential spring is 1/2 k multiplies r minus l square. So for the gravitational potential energy is mgy, and y we have the value is y equal to r cos minus r cos theta. So potential gravity is minus mg r cos theta. So for total potential energy is V equal to 1/2 k multiplied r minus l squared minus mg r cos theta. So for the Lagrangian is L is equal to T minus P. In T is, you can put the T value and V value in here. So we have the L is equal to 1/2 m r dot square plus r square theta dot square minus 1/2 k multiplied r minus l square plus mg l cos theta. So for the Lagrange equation, we have the two coordinates. We will find the coordinate r and coordinate theta because the system works in for the coordinate. For the coordinate r, we have the m r double dot minus m r theta dot square plus k r minus k multiplied r minus l minus mg cos theta equals 0. For coordinate theta, we have the m r squared theta double dot plus 2 mr r dot theta dot plus mgr sin theta equals 0. So this is the final result for the equation, for the Lagrange equation for the system. This equation tells a story. If the mass just moves up and down, we get a spring oscillator. If the length is fixed, it's a pendulum. But when they interact, the result can be periodic, quasi-periodic, or even chaotic. The system is a real-world example of how complex behavior can emerge from simple rules. Why study the system? Because it's model more than just a spring and a mass. In engineering, it relates to vehicle suspension. In space, it resembles satellite dynamic. One system, two motion, infinite behavior. Physics is not always about discovering new particle or distant galaxies. Sometimes it's about looking at something ordinary like a spring and realizing it's not unordinary after all. Thank you for watching. I am Fahry Samsudin, and this is my IWSC 2025 Physics project of pendulum vertical spring, where simplicity meets chaos.